Hey everyone, welcome back to Ask Becca About Space. I'm sorry that I've been on, well, I'm not sorry, but I've been on a brief hiatus. So I'm sorry if you have missed me. I just kind of had a lot of things going on in the past couple of weeks. I finished up some coursework, which involved another lecture delivery and a pretty sizable report on about 4 or 5 months of research. And I also moved to a new apartment. So I'm in the process of completing that moving process. So I'm in the process of processing always. So things have been a little bit wild with me and I am very tired, but I'm good. So I hope things are going pretty well with you as well. I am today going to answer the second two questions that Jackson had. And in my hiatus, Jackson also got himself a new cousin. So that's really cool. Congratulations, Jackson. So, and Joy, obviously, the woman who made the child. Good job. So let's just jump right on in, not waste any time. So Jackson's third question is about stars. And his question is, if in a 2-star solar system the stars collided, what would happen? Oh boy. What wouldn't happen? A better question. No, so this is a great question. So this is not that common of a thing that at least that has been observed, but it has been observed. And a lot of times in binary star systems, you have either two relatively small kind of dwarf stars, or you have a giant star and then a little white dwarf star that are orbiting each other. Those two stars, because they are in such close proximity to each other, very oftentimes mass from the one star will kind of spill over and mass from the other star will kind of spill over, and they'll make this kind of envelope of weird mass transfer that, first of all, is kind of difficult to model, but it's also difficult to understand gravitationally. So it's not very well understood, actually, in the field, how this happens and why. However, I will say that there is a type of supernova explosions that are caused by things like this, basically. So what happens is, this is generally in binary systems with one giant star and one white dwarf star. And as that mass transfer kind of starts to happen between the stars, and instead of being two perfect spheres, they start to kind of reach out towards one another almost gravitationally. So the supernova that I'm talking about, first of all, is called a type 1a supernova. It's also called a pair unstable supernova because it is a pair of unstable stars in an unstable gravitational system. Now, as the mass transfer from the bigger star starts to accumulate on the smaller dwarf star, white dwarf stars are generally pretty quiet as far as stars go. They don't usually have enough mass to be fusing heavier atoms together. So they don't. However, when mass from a giant star accumulates onto a white dwarf star, sometimes, eventually the white dwarf star reaches something that's called the Chandrasekhar limit. And that is a mass limit on allowing the star to basically reignite its fusion capabilities, okay? However, when it does that, long story short, it's extremely unstable and ends up exploding. And so that white dwarf star ends up being basically an instigator star or a progenitor star to a supernova explosion, okay? Now, what happens to the companion star that donated all of that mass to its own demise and that essentially caused the white dwarf star to become so unstable that it couldn't prevent collapse and then explosion? Well, during the explosion, since the companion star is so close to what was the white dwarf star, it's now extremely dangerously close to an explosion, right? So what happens is that companion star is generally just ejected away from the system entirely. And this is kind of along the same lines as what we were talking about last time with wandering planets. This more or less becomes a wandering star because it's ejected by a catastrophic event, something that changed what was at some point at least a locally stable situation. That, of course, became very quickly unstable once the white dwarf star reached that Chandrasekhar limit of mass. Okay, so this is one of the things that can happen when stars either collide or exchange, more likely exchange mass. Collisions do happen, and that is more like when both of the stars are small, both of the stars are white dwarfs, but it's very, very rare. It's more likely that we'll see a giant star with a white dwarf companion, and that giant star donates too much mass to the white dwarf, causing it to be unstable, collapse, explode, and then eject that giant star away from the system. Okay, so that's a great question. All right, your last question is, why are you so interested in the sun? Excellent question. You know I love talking about the sun, so thank you for asking about the sun. So I am interested in the sun for several reasons, but one of the, I guess the foundational reasons why I'm interested in the sun is because of how little we know about it. I think that a lot of the time when like people find out that this is what I do, they're kind of very confused because I wonder if people think that we know more about the sun than we actually do. You know what I mean? We are still trying to figure out actively how the sun transports heat into its atmosphere, because we don't really understand that yet. And that's a big deal, because the only reason life is sustainable on Earth is because we have that source of energy and heat, right? So if we don't really understand how it works, that to me is an issue. So in my job, what I do is I am working on pieces of that puzzle to try and understand the atmospheric heating of the sun. But here's the problem though, because stars generate a lot of heat by fusing atoms together in their core, right? That's fine. That's fairly well understood, more or less. There's a little bit of particle physics and there's a little bit of nuclear physics that you have to kind of nail down in order to understand that, as well as heat transfer. But it's a fairly simple process. All right, hydrogen fusion in the core. There you go. But here's what the sun actually does. There is fusion in the core, yeah. And then the sun radiates heat from those nuclear reactions away for some time. But then instead of radiating that heat away, at the edge of the sun, that heat transfer turns into circular convection currents. So the plasma actually starts rising and sinking in these circular patterns, some of which is caused by the fact that the sun doesn't rotate at the same rate everywhere. And so as the plasma comes up and down and rises up and falls back down and rises up and falls back down, that generates or helps to generate a strong magnetic field, okay? But what about the temperature profile? So in the core, fusing hydrogen into helium right now, that's about 1,000,000 degrees Kelvin. But by the time you reach the top of those convection currents, the surface of the sun, relatively speaking, is about 5,000 degrees or so. Okay, so you've already decreased from 1,000,000 degrees to 5,000 degrees just within the size of the sun. Okay. However, as we reach farther into the sun's atmosphere, which is huge, there is an issue with heating. That is one of the biggest problems in solar physics. It's called the coronal heating problem, because the kind of lower layer of the atmosphere is called the chromosphere. And then there's a transition region, and then you go up to what's called the corona. And that just translates to the word crown. Okay, that's what the sun's upper atmosphere is called. And we can see it from Earth during a total solar eclipse, because that means that the most bright kind of face of the sun is blocked by the moon, and we can see kind of the wispy plasma around it. That's the corona. And it is shaped by the magnetic field. Turns out it is probably also significantly heated by the magnetic field, because where we have kind of a surface temperature of 5,000 degrees, when you get up into the corona, the temperature has jumped to 1,000,000 degrees again. And that has no obvious source of heat, at least in terms of regular heat transfer, okay? That means when there's that big of a jump, that means that there's a problem with what we call the energy budget of the atmosphere. The budget's not balanced. It doesn't make sense how that amount of heat should be that far away from the fusion in the core if fusion is the only source of heat, which we know now that it is not, right? So the consensus now is that the source of that heat jump is likely to be magnetic in nature. At least some parts of that puzzle are probably due to magnetic energy, or what we call magnetohydrodynamics, or basically the motion of a magnetic fluid transferring heat into the atmosphere by magnetically energetic events. Okay, and the sun is a relatively stable star in terms of as it ranks among stars in the universe. It's pretty stable and it's pretty quiet, but it does generate magnetically active events, things like sunspots, things like solar flares, things like what we call coronal mass ejections, which is just a lot of sun plasma ejecting itself from the sun. And when that stuff is facing us, and if it couples correctly to our magnetic field, that's when we get things like northern lights and southern lights and stuff like that. And so the sun is doing things and generating these very hot kind of magnetic events, but we have yet to nail down exactly how much magnetic energy the sun is transferring into the atmosphere, or how much that magnetic energy is heating the atmosphere. So I am working on understanding not necessarily the active regions on the sun, but also the quieter magnetic regions of the sun, because we've learned in the past several decades that those quiet regions also generate a significant amount of heat that we didn't necessarily know about until very recently. Okay, so this is an interesting problem for me, and so that is what I spend my life doing, and I'll let you know when we solve it, hopefully hopefully soon. It's very naive of me to say, but needless to say, I have my work cut out for me. All right, so that's why I study the sun. It's because there are some very huge, glaring, open-ended problems with a star that we very heavily depend on. Okay, so Jackson, thank you for sending in those questions. I really appreciate them. Congratulations again on your new cousin. And if any of you have any other questions, please feel free to send them to me. Our building at work is under construction at the moment, so I'm probably mostly going to be here at home, but I'll have plenty of time to talk to you. Okay, so with that, as we say, of course, keep looking up, and I'll talk to you soon. All right, bye.